When we perform line integration, we need to be careful that we are integrating along the dot product of the line. When we start this, when we integrate this function, x squared plus y I hat plus y cubed j hat, we do so from along this line between these 2 points, In order to do this, we must first find out the direction of this vector. We can do this by subtracting 4, 3, 0 from 4, 0, 0. Final minus initial. When we subtract, we get 0, 3, 0, or simply 3 j hat. If we were to normalize this, 3j over 0 I hat plus plus 0 k hat. I'm showing the entire vector because we won't always have nice clean vectors like this. We divide it by the total distance in order to get a normalized vector. In this case, we get a very simple result, j hat. Our answers will not always be as simple and clear, but this is the correct method to finding the contour vector. So, to integrate from along our first 2 points, I will call this right here A, B, C. For the A integral, I will write our function squared plus y I hat plus y cubed j hat dot j dy. In this case, we are integrating from 0 to 3 in y, whereas x is being held constant at 4 and z is being held constant at 0. This is our A vector integral. If we were to integrate this, the I hat term will completely cancel out. Next, we simply perform the integral, the necessary integration. This will give us y to the 1/4 y to the 4th integrated from y equals 0 to 3 and simply x equals 4, z equals 0. This equals 1/4 3 to the power of 4. Our next integral, using the same method, will be, label this one B, we'll integrate our function x squared plus y I hat plus y to the 3rd j hat Now, we don't yet know what we need to integrate along. If we now, just looking at this, we can work it out like we did last time, or we can simply look at it and notice that the z and the y are constant, so this line is progressing straight along the x-axis. So I can write I hat dx, because that's what the vector differential would be. To evaluate this, we want to integrate x from 0 to 4, while holding y equal to 3 and z equal to 0, because these is held constant between these 2 points. And according to the problem, we're proceeding in a straight line between them. Next, we need to evaluate this integral. Once the dot product of I and j is 0, so we can immediately rule out that point, that part of the factor of the function. Which leaves us with this. We need to integrate. We get 1/3 x cubed plus xy, evaluated from x equals 0 to 4, while holding constant y equals 3, z equals 0. There is no z in this function, but there is a y. We'll change that y to a 3. We also evaluate these limits. We get 1/3 4 to the power 3 plus 3 times 12, 3 times 4, y equals 3, x equals 4, which equals 12. So the answer to this integral is 1/3 4 to the power 3 plus 12. Finally, our last integral is actually remarkably simple, if we will notice a crucial fact. We can set up the integral as before, just as we did previously. However, the direction of the integral is crucial in this example. In this case, we are integrating from 0 to 5 along the z-axis, meaning the vector differential, this, in this case, will be z hat dz. While we can integrate dz, the dotting the rest of the function with k hat, z hat, gives us 0. This completely cancels out. I dot k is 0, j dot k is 0. Answer to the C integral is 0. Lastly, we add up the results of what we got from each integral. So we will have 1/4 3 to the power 4 plus 1/3 4 to the power 3 plus 0, leaving us with this. If we evaluate this on a calculator, we'll find this is equal to 53.583. That is a scalar quantity and is what this line integral is equal to.